Let's start off by logging into the Amazon SageMaker console and begin by launching a new notebook instance. So create a notebook instances and give an appropriate name for the notebook that we wish to create. Under IAM role, click create a new role and select any S3 bucket and click create role. Apart from that, we can go ahead and review the settings before creating the new notebook instance, and let's wait for the instance to get generated. In our case, we'll be falling back to the original notebook that we have created to continue with the demo going forward. Let's wait for the instance to load up. Let's go ahead and launch a new notebook. Same here. In our case, for demo, we'll be falling back to the original notebook that we have in place already. Next, let's look at uploading the raw dataset into the S3 bucket. We'll be using the AWS CLI tool to upload the dataset to the corresponding S3 bucket. The first task is to perform exploratory data analysis. In the Python file, the IAM role is defined. We also have the bucket name specified as well as the imported libraries being imported, and then we plot the data using the C1 library, which is a data visualization library in Python based on matplotlib, and as we can see we get a grid of plots. Here blue color represents class 0 and the red color represents class 1. Next, we explore several device machine learning algorithms. We start off with the XGB algorithm. XGBoost is a popular and efficient open source implementation of the gradient boosted trees algorithm. Gradient boosting is a supervised learning algorithm that attempts to accurately predict a target variable by combining an ensemble of estimates from a set of simpler, weaker models. We select the first 200 rows of class 0 and the first 200 rows of class 1 as a test set and rest of the data as a training set. We build a model based on the chosen algorithm, which is XGB in our case here, and then train and test the model. We then report the training accuracy, test accuracy, and the test score. Uh, Here the first 200 rows of class 0 and first 200 rows of class 1 are selected as a test data. The objects can be concatenated along the particular axis using pandas.concat, and the index is used to represent the data values along with class. The train features as values of 4 variables: skewness, kurtosis, entropy, and variance. The train labels as label values like class 0, class 1. The training data is uploaded into the S3 bucket in a suitable format that can be used by the model later on. We then define the containers which point to the relevant resources. In our case, the ones which have the XGBoost resources available, and then we launch an estimator session. We define the required hyperparameters of the XGBoost algorithm, and then we fit using fit the model using the training input. And once the training model has been generated, we deploy a predictor handle using which we can invoke the predict functionality to first with the test data and then retrieve the confusion matrix from which we can calculate the test accuracy and the F1 score. These are now highlighted on the screen for the XGBoost algorithm, and we can also calculate the training accuracy by calling the predict functionality with the training data array, and we have the training accuracy. Next, let's be sure to define a function to delete the endpoint once we are done using it in order to avoid building up unnecessary charges later on. Next, let's check out the linear learner algorithm. Amazon calls the linear regression and logistic regression algorithms linear learner. Linear models are supervised learning algorithms used for solving either classification or regression problems. The algorithm learns a linear function, or for classification problems, a linear threshold function, and maps a vector to an approximation of the label. The process being followed here is pretty much similar to what we have done for previously while working with the XGBoost algorithm, which is splitting up the data into training sets and the test sets, uploading the data into the S3 bucket so that it can be used in a sensible format by the model later on. And then once again we define the containers which have the linear learner resources available on them, followed by which we launch an estimator session. We also define the hyperparameters for the linear model with the predictor type being a binary classifier in this case here. And then we go ahead and fit the model with the training data, followed by which we deploy a predictor instance. And with the predictor instance, we first predict the test data array, and from which we generate the confusion matrix and go on to calculate the test accuracy and the F1 score. And then we use the same predictor handle to predict with the training data as well, and we go on to calculate the training accuracy of the model. We get to see the relevant logs. And here we have the final output being displayed on the screen with the test accuracy and the test F1 score alongside the training accuracy. We can see that the linear regression training model certainly is better than the XGBoost algorithm for this particular data set. Next, we check out the k nearest neighbors algorithm, which is an index-based algorithm. It uses a non-parametric method for classification or regression, and training with the KNN algorithm has three steps, which is mainly sampling, dimension reduction, and index building. Sampling reduces the size of the initial dataset so that it fits into memory. For dimension reduction, the algorithm decreases the feature dimension of the data to reduce the footprint of the KNN model in memory and inference latency. And the index enables efficient lookups of distances between points whose values or class labels have not yet been determined, and the k nearest points to use for inference. The steps to be followed here is pretty similar to that that was followed for the previous two models. Basically, we go ahead and split the data into the test set and the training set, and then we upload the training set to the S3 bucket. And once that is done, we define the hyperparams list. In our case here, we will be iterating across a number of values for k, typically ranging from 15 to 55 in steps of 5. And we have made sure that the resources being picked up in this case here are capable of supporting modeling with the KNN algorithm. And we launch an estimator session with iterating across each of the entries in the hyperparams list, and we fit the model with the training data, and then we deploy a predictor handle with which we and use it to predict the test data first, thus generating the confusion metrics from which we can calculate the test accuracy and the F1 score. Following which we use the same predict handle to predict the training data, and in turn helps us generate the confusion metrics from which we can eventually report the train accuracy. And this is repeated for various values of k, and after each instance we make sure that the endpoint is terminated. So this is the output for k equal to 15, and we have the output highlighted on the console screen, and these are this is the output for k equal to 20. And once again we have the output highlighted on the screen. Next we have the logs for k equal to 25, and we start to see that the test accuracy starts to drop as the value of k goes beyond 20 in our case here. So even for k equal to 30, we see that the test accuracy and the training accuracy is no longer 100%, and this is again the output for k equal to 35. Now we have the logs for the k equal to 40. And we see that the test accuracy has once again dropped. Now we move to k equal to 45. And output associated with it, and this is for k equal to 50. And we have the corresponding output, and we see that the test accuracy has fallen once again, uh, which kind of signifies the fact that it's best to stick to the initial value, stick to a value of k equal to 15 or 20. In case of the dataset we have in our hands here. We see that KNN algorithm fares the best in our case here, followed by linear learner and XGBoost being the least preferable. Once done, be sure to clean up any endpoints that may still be present from the dashboard in order to prevent raking up unnecessary additional costs. Now, the AWS Deep Learning AMIs provide machine learning practitioners and researchers with the infrastructure and tools to accelerate deep learning in cloud at any scale. These are loaded with deep learning frameworks like TensorFlow, Keras, etc., which can be used for building models, training, and working with large-scale datasets. In this part, we use the deep learning AMI to perform deep learning computation on the banknote authentication data using one of the deep learning frameworks available. Let's begin by logging into the EC2 dashboard and launching a new AMI instance. We'll be launching a deep learning AMI Ubuntu instance in our case here. Click continue, and we can go ahead and choose an instance type. We'll be going with C5 large instance in our case here, and let's go ahead and review the instance details and launch the new instance. Let's make sure we have access to the keypad. Let's wait for the instance to launch. Next, let's launch a Jupyter instance on the remote machine. Let's log into the machine by using SSH, and once we have logged into the machine, let's generate a new set of SSL certificates. And once this is done, let us launch a new Jupyter Notebook session with the new accessible certificate that we had just created. Uh, Next, let's look at connecting to this new Jupyter Notebook from the client machine. Let's first set up an SSH tunnel mapping the specific port, and once this is done, we should be able to access the Jupyter Notebook instance through the web browser on our machine. Once we have logged in, let's create a new notebook and the TensorFlow instance. For the purpose of the demo, we'll be switching over to our existing notebook, which is again in the TensorFlow instance. And under the root folder, we also get to see a data folder within which we have the banknote authentication dataset. Coming back to our TensorFlow notebook environment, we have the code for deep learning computation on the banknote authentication data. We have imported all the necessary libraries. We've used pandas to read the data we uploaded and converted it into data frames, and we have checked the dimensionality and the head of the data frame. And we have created a new data frame with the class field removed, and we have used a standard scaler to standardize the feature by removing the mean and scaling to unit variance. And standardization of a dataset is one of the common requirements for machine learning estimators. We then stored the scaled features to a separate data frame, and we have renamed the class attribute to authentic and created forced attribute based on the authentic attribute. Next, we go ahead and set the TensorFlow and neural network parameters. The learning rate determines how fast the weights change. The training epochs. One epoch is when an entire dataset is passed forward and backward through the neural network only once. The batch size determines the total number of training examples present in a single batch. And n underscore hidden are the nodes in hidden layers. The input shape is forced since we have features here, and there are two classes, namely authentic and forged. We use a class of feed-forward artificial neural network called multi-layer perceptron. It consists of three layers: input, hidden, and output layers. Using the multi-layer perceptron function, the weights and the biases, we construct the model. Once we run the script, we get to see the output logs, and the epoch counts, And we have train accuracy, the test accuracy, and the test F1 score reported. Be sure to terminate any instances in order to avoid unnecessary charges.